We've already seen how converting from Cartesian coordinates into polar coordinates, things become a lot easier to work with. Now we are going to convert from Cartesian coordinates into spherical coordinates. And we are going to convert from Cartesian coordinates into spherical coordinates. Things become a lot easier to work with. So when you look at this, this is a double integral. So your xy plane, becomes your domain. Here we're working with a triple integral. So your xy and z 3D space becomes your domain. So this 3D space becomes your domain. So converting from Cartesian coordinates into cylindrical coordinates, we would use cylinders to reference any point in 3D space. So let's say you want to reference this point here. Let's say you want to reference this point in Cartesian coordinates. You would just specify the x, y, and z value. That would allow you to reference any point in 3D space. Well, in cylindrical form, you would use cylinders to reference any point in 3D space. So here you would specify the radius of the cylinder, which is this r here, and then you would specify the angle here, theta, and then you would specify the height of the cylinder, which is your z. By using cylinders, we can reference any point in 3D space. Now let's look at spherical. So in spherical, we would use spheres to reference any point in space. So let's say we want to reference this point here. Remember, these are your spheres, not your 2D circles, but in your mind picture spheres, not circles. So to reference any point in 3D space, we would specify the radius of the sphere, which we are going to call rho, and then we would specify the angle it makes with the z-axis. So this angle here is phi. We would specify the angle phi, and then we would specify the angle here, theta. So with these three arguments, we can reference any point in 3D space. Okay, so hang on. So going back to here, going back to double integral, converting from Cartesian into polar form, we would transform this into this thing here. By demanding this, we would transform this into here, and then we've already looked at why you would have this weird r in here. So in cylindrical form, this is your dv. This is your dv. Well, dv becomes this thing here. Still, you've got this weird r in here, and then in spherical form, this dv, the change in the volume, becomes this weird complicated thing. Even though it looks ugly at the moment, there are times when it becomes easier to work with, if you work in spheres rather than in our traditional Cartesian form. So hang on, we need to try and understand why it becomes this ugly thing here. In cylindrical coordinates, this dv becomes this thing here. This is easy to understand, but this thing here is a lot more difficult to understand. Okay, so let's look at the easy case for the time being. So with cylindrical coordinates, hang on, let me think. With cylindrical coordinates, this is in Cartesian form. This is your dA here. If you want the change in the volume, you would just simply times it by the change in the height. So really, your dv in Cartesian form, it would simply be dx times dy times dz. We can accept this by now. When you look at this area here, if you convert it into polar form, which we've already seen, let's say this, you're looking at this area here. The change in the area is simply dr, the change in the radius, times with the change in the angle, this angle here, and then you stick this r. We've already seen this, and by now I'm expecting you to be able to accept this. So the change in the area has this kind of a relationship. And we've already seen this, so I'm expecting you to be able to accept this. Well, in cylindrical form, you're working with cylinders. So a change in the volume of a cylinder. So once you've got this area here, which is this area here, you simply multiply it by the change in the height. So that's really this thing here. So to accept that the change in the volume has this kind of a relationship is quite simple. When it comes to spherical coordinates, it becomes a lot more difficult, because let's say you've got a change in the radius, which is this thing here. So this is the rho here, and then you'll remember this phi here is the angle which it makes with the the phi here is the angle which it makes with the z-axis. So that's this angle here. That's this angle here. So this is your, hang on, this is going to be your, this angle here, this, hang on, this angle here, I hope you can see, is your delta phi, which is this bit here. And then remember, this angle here is is your theta. So this is your d theta here. Hang on, this is your delta theta. Well, a small change in the radius and a small change in this angle here and a small change in this angle here has this kind of a relationship. So this is has this kind of a relationship here. So this is your dV. It becomes, and at the moment you don't know why this is the case here. We will look at it in the next video, but I hope you can see that that when it comes to spheres, a change in the volume has a weird relationship regarding the change in the radius, the change in the angle here, and the change in the angle here. It has a weird relationship here, which I will try and convince you as time goes on. Okay, I hope you, for the time being, I just hope that you can accept that it is a weird, there's some sort of weird relationship when it comes to the change in the volume. It's this weird, complicated thing here, and at the moment you don't know why it's weird, but just know that the weirdness exists, because when it comes to spheres it becomes a lot more complicated. When it's cylinders, the dV, when it comes to cylinders, the dV is quite straightforward, because we already know that the dA has this relationship. So when it comes to the dV, all you need to do is stick the change in the height, and then it becomes this thing here. With spheres, it becomes a lot more complicated, and I will continue in the next video. Okay, just know that at the moment it's weird, it's complicated, and you don't fully understand why. I will continue in the next video. Okay.